Welcome back to ECE 320A. We're in Unit 12, and this unit is dealing with two ports. In this particular video, what we want to examine is actually a circuit that contains a dependent source and illustrate, maybe not going through all the details, but at least setting up the problem so that you could actually find the 4 Z parameters associated with a circuit that now possesses or contains a dependent source. And that now is this dependent current source that is actually a function of the voltage at the input port of our two-port network. And we want to now see if we can find expressions for Z11, Z12, Z22, and Z21, our 4 Z parameters, which involves having the I1 and the I2 as independent variables. And now what we can actually do is figure out how do we analyze this circuit in order to try to find these equations relating V1, V2, I1, and I2 so that we can now solve for the Z's. And the way this is set up, let's go ahead and just identify two nodes. There's node A, and we'll call that potential V sub A, and we'll call this node, or label that node, as having voltage V sub B. And now we should be able to write some equations to try to find the standard form of V1, V2 equaling this Z matrix times I1, I2. But now that we've identified these node voltages, let's go ahead and then write a KCL equation at both of those nodes. If we look at KCL at node A, we then have I1 coming in from the left, and that's equal to the current going down through R sub 1, or that's now V sub A over R sub 1, plus this current going to the right from left to right through R sub 2, which is now going to be defined by looking at the voltage dropped across R2 from left to right, and that's V sub A minus V sub B over R sub 2. There's one equation, one KCL equation in terms of the two node voltages that we've defined, V sub A and V sub B. If we now look at writing a node equation, so this isn't very difficult, we just have to basically keep track of what we're doing. Now let's find or write a KCL equation at V sub B, and we could now say that I sub 2 coming in from the right is going to equal the current going down in the vertical branch, but that's now just defined by this dependent current source, which it's dependent on a voltage, but this is now beta V1 plus the current going from right to left through R sub 2, and that's now V sub B minus V sub A. Our voltage drop is from right to left divided by R sub 2. And now we've really defined the relationships for currents and voltages in this particular circuit that is a two-port network. But what we have is equations involving V1, V sub A, V sub B, and I1 and I2. We actually need equations that contain I1, I2, V1, and V sub 2. And one way we can do that is now see if we can express or replace v sub a and v sub b in terms of v1, v2, I1, and I2. We need to eliminate v sub a and v sub b. But I think you can see on the left anyway that v sub 1 is in fact v sub a. Here are some observations then that we can make to try to help us find these two equations that we need containing the four variables that we want. First is that v sub a is equal to v sub 1, and now we have a way of eliminating v sub a from these two equations. We simply replace v sub a everywhere with v sub 1. Check. Now we can actually find, or can we find, a relationship between v sub 2 and v sub b. We could do a KVL maybe around and avoid that particular dependent source, or let's just write I sub 2, that current going from right to left, through R sub 3 in terms of R sub 3, V sub 2, V sub B, and I sub 2, and then solve for V sub B. We know I sub 2 is V sub 2 minus V sub B over R sub 3. So our second observation then is that I sub 2 from right to left is V sub 2 minus V sub B over R sub 3. Or we can now say then that V sub B, solving for V sub B, we've multiplied both sides through by R sub 3 and maybe negated the signs or moved V sub B to one side, isolated V sub B, and now we have V sub 2 minus R sub 3, I sub 2. And now we have a way or an expression for V sub B in terms of the parameters that we need, or the variables that we need, in particular V sub 2 and I sub 2. And now we have a way to rewrite equations A and B in terms of V1, V2, I1, and I2. If we do that, then I sub 1, that's our A equation, is V1 over R1 plus V1 minus V sub B, but V sub B is V sub 2 minus R sub 3 I sub 2 all over R sub 2. And now we have one equation in terms of I1, V1, V2, and I2. We've simply used this to get rid of V sub B. So here's one of our equations that we can use to try to identify V's equal to Z times I. From the second equation, or from equation B, we now can rewrite that as I sub 2 is equal to beta V sub 1 plus, and now we had V sub B, which is V sub 2 minus R sub 3 I sub 2 minus V sub 1. Better make sure I'm doing the right thing. It was V sub B minus V sub A, and V sub A is V sub 1 all over R sub 2. And that's now our second equation that only contains V1, V2, I1, and I2. I hope you can see then that from these we now have some expressions, or two equations. We could put all of these terms on one side or the other and then put the i's on another side, but I hope you can see that from equation 1 we have something that we could now multiply V1 and V2 by on the left and put all of our i's on the right. So we have something over here, and one of those pieces, actually, if you look at this piece, that would then be 1 over r sub 1. And we have another V1, which is plus 1 over r sub 2. And that's now what multiplies V1. And what do we have for I sub 1? Well, we just have I1, and then we also have an I sub 2 that will be subtracted once we move it to the other side, r sub 3, I sub 2. And that will be what we're meaning by f sub 1, a function of I1 and I2. Is that clear? This is now, if we now have isolated the V1 and V2 on one side, then we had an I1, and we now also have an I2. That was a plus over here, taking the minus of a minus, so that when we move it over to the other side, that's now minus r sub 3, I sub 2. And that's what I mean by I had a function, f sub 1, some linear combination of I sub 1 and I sub 2. And what's scaling v sub 2? Well, what's scaling v sub 2, if I'm seeing all of the different terms, is just this minus 1 over r sub 2. Oh, and I missed that r sub 2, did I not? So in this particular expression, I had an r sub 2 in the basement of r sub 3 over r sub 2. I had a ratio of r sub 3 over r sub 2 scaling I sub 2. I hope you caught that. But that's now how we would convert that first equation into this matrix formulation. And the reason I'm doing this matrix formulation is now I want to actually invert this matrix that's some combination of r's coming in betas from this circuit, and that will then allow me to have a V1, V2. I've now inverted that in terms of something scaling once I've now sort of put this together. Really, this will be some matrix that now scales I1 and I sub 2, which would then be 1 and a minus r sub 3 over r sub 2. That's going to now be the matrix, that 2 by 2 matrix that gets scaled on or hit on the left by the inverse of this 2 by 2 matrix, and that will then leave me with some 2 by 2 matrix whose 4 elements I can then refer to as the different z parameters. And in this particular case, if you do the math, hopefully you'll obtain then for z11 r1 over 1 plus beta r sub 1. That's z sub 1. Z sub 1, 2, r1 over 1 plus beta r1. And z sub 2, 1 is now r1 minus beta r1, r2 over 1 plus beta r1. And you can see now that because of that dependent source, the off-diagonal terms are not equal like they have been in some of our previous examples, and the z22 is now r1 plus r sub 2 plus r sub 3 plus beta r1 r sub 3 over the same denominator. No, this one's a little different. This is now r sub 2 times 1 plus beta r sub 1. And that's now our z parameters. if those have fixed betas and fixed R's, 1s, and R2s and R3s, those will just be some numbers for the different 4Z parameters that result from this two-port network that contains a dependent source. And that is then our two-port parameters in the appropriate locations, Z11 through Z sub 22.